One of you check whether it is started or not. It is. Yes, you can start.
Good evening, all of you. I extend a hearty welcome to everyone for today's talk. This event is organized by Karilief, a math club, in collaboration with MTTS Trust. Our distinguished speaker for today is Dr. Kiran Behera. A very warm welcome to you, sir. Today, sir will be presenting a talk on what are continued fractions. So we know that continued fraction arise in many areas in mathematics. So today he'll take us to the origin of all that and then conclude with few project ideas. Before we delve into the talk, I would like to briefly introduce about sir. So sir is engaged with many esteemed institutions. He has done his MSc and PhD from IIT Roorkee. He has completed his postdoc from IISc Bangalore. And one of the proud moment to all of us is he is an MTTS alumni. Welcome to you, sir. So before the talk begins, I would like to bring this instructions to all of you that kindly refrain yourself from unmuting. If you have any questions, there is an option called raise hand, but raise hand, kindly make use of it. For those who are watching it on YouTube, you can post your questions on the comment section. We'll make sure that those reach the speaker. Over to you, sir.
Thank you, Bhumika. So thank you, Karilief, for inviting me for this lecture. It's always feels good to be back with. I consider MTTS as one of my alumni. So I attended the MTTS level O camp way back in 2006 in Jadavpur University, and then in the last 2 or 3 years, I was a student back then, and I became a mentor, and then finally a resource person. So I can see my career grow with MTTS. So today's topic, it's a very classical subject called continued fractions. We'll not go into much of the theory or results or details. We'll look at examples, just the basic ideas and notions of the continued fractions and what are its applications, what are its advantages, and then we'll end with some a bit advanced topic. Okay, so let me share my screen. So let us start. I'll not be like giving a PPT talk. I don't like it. So I will write, and I hope you all will be with me as we move along. So today's topic is continued fractions. So what is one's first exposure to continued fractions? We are already exposed to a continued fractions in our school days. So it was the question this: if x equals 1 by 1 plus 1 by 1 plus 1 by 1 plus and so on, if x equal is, find x. So this was a question many of us would have solved in the school days. So what we do, we put x, and since this part so this part is same as x, so what we do, we put x equals 1 by 1 plus x. This gives us the quadratic. We then convert this into a quadratic equation: x plus x square minus 1 equals 0. and then by the quadratic formula we find x equal to what, root 5 plus minus 1 by 2, right? So this is the simplest case of a continued fraction. We'll come back to it at the end of our discussion, why this continued fraction is important, right? And will be interesting. We'll connect it to something really very interesting. So what our goal for today is, so like here we have numbers. I'll be discussing a structure or a mathematical structure of this form. So here instead of numbers, I have functions. Right. So x can be a real number, a natural number. What do we understand by this fraction being continued? So that is why we call it the continued fractions. For all practical reasons, ai and bix are polynomials of degree 1. So in most of the practical examples that arises, this bix, aix, and bix are linear polynomials. So we'll discuss the initial or preliminary theory of this structure and how to formally define a continued fractions, right? So let us look at some of the motivating examples or the early origins of continued fractions. So first is Euclid's algorithm for GCD. Now, for example, I want to find the GCD of 43 and 19. So what was Euclid's algorithm? So it is 43. So Euclid's algorithm was 43 equals 2 into 19 plus 5. And then you divide the quotient by the remainder. 3 into 5 plus 4. 5 equals 1 into 4 plus 1. And then this 4 equals 1 into 4 plus 0. Sorry, 4 into 1. It should be 4 into 1. I'll divide the quotient 4 into 1 plus 0. So whatever is the quotient I get at the end, it becomes the GCD. So this was Euclid's algorithm. So now, though Euclid did not use continued fractions, the later mathematicians connected this algorithm to a continued fraction of this form. So 43 by 19, if I divide this equation both side by 19, I will get 2 plus 5 by 19, right? And this is 2 plus 1 by 19 by 5. Now divide this equation by 5. I will get 2 plus 1 by 19 by 5 is 3 plus 4 by 5. And this again I divide by 2 by 3 plus 1 by 5. 1 divided by 5 by 4. Divide this equation by 5 by 4. I get 2 plus 1 by 3 plus 1 by 1 plus 1 by 4. So what we have is I have converted a rational number into a continued fractions, a fraction that continues. And these are these 2, 3, 1, 4. These are the coefficients that I have obtained here. 2, 3, 1, 4. Right. So now, how does this help? So it became a test for rationality. If you consider a rational number of this form, so if you consider a rational number of this form, p by q, and convert it into a continued fraction using Euclid's algorithm, it always terminates. Right? Intuition. This is clear. If I have if I have a rational number 43 by 19, 1 by 2, 5 by 2, anything, you use this algorithm will terminate. And so the corresponding continued fraction that we obtain will also be terminate. So this continued fraction always terminates. And how it helps? If the continued fraction doesn't terminate, then the real number it represents is not rational. Right? This is kind of a contrapositive of this statement. If it is rational, the continued fraction will terminate. If the continued fraction doesn't terminate, it represents a irrational number. Right? So irrational number or non-terminating continued fraction will represent irrational number. So this became a kind of test to check whether a real number is rational and or irrational. If you have a continued fraction of natural numbers that doesn't terminate, it represents, or we can say it always converges to a irrational number. So this is how initially, very initial stage, these continued fractions were used by the Greek mathematicians or the Chinese mathematicians, even the Indian mathematicians, right? So, so again, right, but what is the use? So for example, I have a irrational number, right? Okay, I'll come to this. What is the use of this? That a non-terminating fraction represents a irrational number, right? So for example, this is an irrational number. I have R irrational, and this R is represented by this rational a continued fraction of this form, a1 by b1 plus a2 by b2 plus a3 by b3 and so, right? Where a1 and bi, ai and bi are also natural number. Right? So what we have here is the idea of rational approximation. So for this continued fraction, first approximant is a1 by b1, second is a2 by b2, third is a3 by b3, right? So what we have on the left hand side, I have an irrational number r. On the right hand side, I have a sequence of rational numbers. And the fun fact is an by bn, it converges in some sense, will not go into the details, to r as n goes to infinity, right? So what we have constructed? We have constructed a sequence of rational approximates to an irrational number, a sequence of rational numbers that converges to r. So this is one of the like biggest achievement of this continued fractions. They are used to represent irrational numbers by rational numbers. For example, we will see why do we take pi equal to 22/7. So left hand side is an irrational number, right hand side is a rational number. So where does this come from? Right. We'll conclude with this. So let us take another example. Again, a very interesting one, a concrete case. So I start with √2 - 1 into √2 + 1 is a square minus b square. 2 - 1 is 1. So this will imply √2 - 1 is 1/1 plus √2, and this is 1/2 plus √2 - 1. So √2 - 1 is 1/2 plus √2 - 1. So I'll substitute the value for √2 - 1. 1/1/2 plus √2 - 1. And I can continue. So what I finally have is √2 - 1 is 1/2 plus 1/2 plus 1/2 plus, and so on. Right. So again, see on the left hand side, or if I bring 1 to here, I will have √2 equals 1 plus this. So on the left hand side, I have the irrational number that we all start with, √2. On the right hand side, I have a continued fraction. So again, approximates, rational approximates. Right. So first is 1, second 1 plus 1/2. I'll stop here. 1/1 plus 2. So it is 3/2, 1.5. Third, 1 plus 1/2 plus 1/2. So this is 7/5. This is 1.4. Then fourth, let me change the color. Fourth is, I'll simplify the fraction, is 17/12. This is 1.4166. Fifth is 41/29. This is 1.41379. Sixth is 99/70, which is 1.414285. Right. So what we have seen is on the left hand side, √2 is all rational approximates. They converge to √2. Right. So this is again a concrete example of approximating the irrational number √2 by a sequence of rational numbers. So this is the sequence: 1, 3/2, 7/5, 17/12, 41/29, 99/70, and so on. And what like computations show that already at this level, 6th level, the error of the actual value of √2 is less than equal to 0.000408. Right. So they not only provide a rational approximation to irrational numbers, their convergence is also quite fast. So this is like what really got people interested in continued fractions. And not only irrational numbers, we can also find continued fractions of functions. So let us consider one such function. So again, 1 plus x. under root 1 plus x minus 1 under root 1 plus x plus 1. Again, f square plus b square is x. So this implies under root 1 plus x minus 1 is 1 by 1 plus under root 1 plus x plus 1. Sorry, this will be minus 1. Under root 1 plus x minus 1 is x by 2 plus, sorry, this will be 2 minus 1, right? So I bring this below, right? X. So this is what I get. Now I convert this into a continued fraction, right? So I'll replace the value here with the value here. So what I will get is under root 1 plus x minus 1 is x by 2 x by 2 plus x by 2 plus x by 2 plus x by 2 and so on, right? So so this is a function of x and this is its continued fraction representation. So what we have is approximates again, and we'll discuss what these approximates converge to. Approximates, right? So first is x by 2, second is x by 2 plus x by 2. So this gives me 2x by x plus 2. Third is x by 2 plus x by 2 plus x by 2, and this gives me x square plus 4x by 4x.
Kiran, the first one is the second one should be, I think it should be what, 2x plus 4, is it? 2x by x plus 4?
Correct. Thanks. 2x
Yeah.
by x plus 4. Should be 2x by x plus. Right. So so we have a continued fraction. So on the left hand side I have a function, on the right hand side I have a sequence of rational approximate that converge to f of x in some sense. So you substitute the value of x, let's say x equal to 1 or x equal to anything, you substitute the value of x on the right hand side, you will get your sequence of rational numbers that converges to, if I put x equal to 1, I will get a sequence of rational numbers to the irrational numbers root 2 minus 1. So this is the idea. But why this continued fraction x is important? For example, under root 1 plus x minus 1. I also have the Taylor series expansion for this function f of x. I have the convergence criteria. So this is the Taylor series expansion is f of 0 plus f dash of 0 x plus f double dash of 0 by 2 factorial x square plus f triple dash 0 by 3 factorial x cube, right? I'm talking about Taylor series expansion. Taylor series around origin. So if I actually compute this, I get under root 1 plus x minus 1 is f of 0. F of 0 is under root 1 minus 1 is 0. So to start with 1 by 2x minus 1 by 8x square plus 1 by 16x cube minus 5 by 128 x to the power 4 and so on. So this is the Taylor series expansion of this function fx. Now this function fx, if we look at the convergence, so this fx, so this series converges for mod x less than 1, diverges for mod x greater than 1. And what else? The approximants in the Taylor series are polynomial. So the first approximant is 1 by 2x. The second is 1 by 2x minus 1 by 8x square. The third is 1 by 2x minus 1 by 8x square plus 1 by 16x cube and so on, right? So while in the continued fraction or in the Taylor series expansion, we have a sequence of polynomials that converge to the function. In case of continued fractions, we have a sequence of rational functions that converges to the functions. So this is the difference between a Taylor series expansion and the continued fraction expansion. Polynomial approximants in one case, rational approximants in the other case. But why, if a Taylor series is there, why study continued fractions? Because continued fractions are in a way difficult to derive. The interesting part is there are two interesting facts. First is numerical experiments. They suggest that continued fraction converges faster to fx than Taylor series, right? So the rational approximates that one gets by continued fraction, it converges faster to fx for a particular value of x than the polynomial approximate that we obtain from Taylor series. This is one advantage. Second advantage is, so again, that function under root 1 plus x minus 1, the Taylor series real case. If x is real, the convergence is this, minus 1 plus 1. But for the continued fraction, real case, it will converge for all number greater than minus 1. For example, in the Taylor series, in this Taylor series, if I put x equal to 3, it doesn't make sense because this series converges only for mod x less than 1, right? So x equal to 3 doesn't make sense in this case, but x equal to 3 makes sense in this continued fraction or in the series of these rational approximates. So what it happens, or what the continued fraction expansion does, it increases the domain of convergence. So the domain of convergence was this for Taylor series. For continued fraction in the real case, this is the domain of convergence, minus 1 to infinity. And in the complex case, the Taylor series converges only for mod z less than 1 within the unit disk. But in the continued fraction, it converges for all z except this part. Right. So continued fraction converges for all z except the ray minus infinity to minus 1, right? So continued fractions are important because One, in some cases, they converge faster than the polynomial approximations that we obtain from Taylor series. Second, and more importantly, it increases the domain of convergence. So these are the two motivating examples. So let us formally define what is a continued fraction, and then we'll see what else we can do. Okay. Let us skip the formal definition. It is too theoretical. I don't want to spend time. We'll work with examples. Right. So what the example that is so now, it has a Taylor series expansion. It has a continued fraction expansion. So the Taylor series expansion, so fx, f of z, it has a Taylor series or a power series, and it also has a continued fraction expansion, right? So power series and continued fraction from the same function fz. Now, is there a relation between power series and continued fraction expansion? So by that, what I mean is, can I come from power series to continued fraction, and can I convert a continued fraction to a power series? So these are the two questions that we'll discuss, right? So power series, so given a power series to continued fractions. So now I don't know what is fz. I only have the power series. So can I convert it into a continued fraction? From the continued fraction, I will get a sequence of rational approximants, and then I will check to which function the rational approximants converge, and that way I will get fz, right? So now I only have power series, and I want to convert it into a continued fraction. So what is the idea? The idea is, so if I have c0 plus c1x plus c2x squared plus c3x cubed and so on, write this as c0 plus c1x 1 plus c2 by c1x plus c3 by c1 x squared on c0 plus c1x by 1 plus c2 by c1x plus c3 by c1 x squared plus and to the power minus 1. So what I will do, I will expand. This is of the form 1 plus j minus 1. I will expand 1 plus j to the power minus 1. I will get c0 plus c1x by 1 plus 1 minus, it should be 1 minus 1 minus c2 by c1x minus c3 by c1x square minus c4 by c1x cube minus so on. Next step, what I did earlier, c1x 1 minus, take this common, so 1 minus c2 by c1x 1 plus c3 by c2x plus c4 by c2x square so on. Bring this to its denominator and proceed. So finally, what continued fraction I get? So if I start with c0 plus c1x plus c2x square plus c3x cube, I'll get this continued fraction c0 plus c1x by 1 minus c2 by c1x by 1 minus c3 by c2x by 1 minus c4 by c3x by and so on, right? So this is how we convert a power series to a continued fraction. So we know the power series of many special functions like exponential function, sine, cos, tan, log, right? So we use their power series to convert them into continued fractions. So let us look at the continued fraction expansions of some special functions. So e to the power z. So what we have, I have the power series expansion of e to the power z. I have converted it into the continued fraction, this 1 plus z by 1 minus z plus z by 2 minus z plus 2z by 3 minus z plus 3z by 4 minus z plus and so on, right? So again, I have two representations of e to the power z exponential. First, the power series representations. If I terminate the power series, I'll get a sequence of polynomial approximation to polynomial approximates to e to the power z. In the second case, I will continue fraction expansion. If I terminate it, I'll get a sequence of rational approximates to e to the power z. So in this case, the rational approximates continued fraction is not much used, because if I have a sequence of rational functions, it will have a pole, right? The point at which the denominator vanishes. But this e to the power z is an entire function. So I am trying to approximate an entire function by a sequence of functions that have singularities. So which doesn't make sense. So in this case, the rational approximation to e to the power z is not required, but anyway, we have the continued fraction expansion. Similarly, another example, ln1 plus z. I have the power series expansion and I have converted it into the continued fraction 1 plus z by 2 by 1 plus z by 6 by 1 plus 2z by 6 by 1 plus. It goes on like this, and it converges for this part. Argument of 1 plus z, it should be less than pi, right? So similarly, like these two examples, we will have continued fraction expansions for any function that has a power series representation. We'll have two representations. So now let us discuss how do you come from continued fraction to a power series, right? So power series to continued fraction. Now how we come from continued fraction to power series. So again, let us start with this ln1 plus z. So what we had, z by 1 plus z by 2 by 1 plus z by 6 by 1 plus 2z by 6 and so on, right? So how do I convert this continued fraction to a power series, right? So so what I do, first approximate is 1, z by 1, and I write this as z plus 0 z square plus 0 z cube plus this. I underline this, I will say y. Then second is z plus 1 plus z by 2. If you simplify this, you will get z minus z square by 2. So how do I simplify? Let me write this there. So it is z times 1 plus z by 2 inverse. So you expand this, you multiply z, you will get this z minus z square by 2 plus z cube by 4 minus z to the power 4 by 8 plus. And let me underline this part, right? I underline here z, I underline here z. So what about the second approximate, third? third is z by 1 plus z by 2 by 1 plus z by 6. And if you simplify, use something like this, you will get this z by z square by 2 plus z cube by 3 minus 2z to the power 4 by 9 plus something. Let me underline this. Right. So what I have is, so what is the power series of z? ln1 plus z is z minus z square by 2 plus z cube by 3 minus z to the power 4 by 4 and so on. So what I have is the approximants agrees with the power series of ln1 plus z as the order increases. So the first approximant, it increases up to first term. The second approximant, it increases, it corresponds or it is equal till the second term. The third approximant, it is equal till the fourth term, and this remains true for n. The nth approximant will, the terms in the nth approximant will agree up to the n terms in the power series expansion. So this is what we say the correspondence power series continued fraction correspondence. So a continued fraction corresponds to a power series expansion. How? Take the rational approximation, take the rational approximants of the continued fraction, expand it into a power series, and the nth approximant will agree with n terms of power series. So this is how we go from power series to continued fraction and continued fraction to power series. Now, there are various right. So now we come to the last topic. So there are various things that you can discuss with continued fraction, but I will discuss one important topic that is really has applications, and it is called path approximation. We will see how this relates to continued fraction. So for example, I start with fz. I have a function fz. It is analytic. I have its Taylor series expansion. So C naught plus C1 z minus a around a, Taylor series around the point a. C2 z minus a square and so on, right? So this is the Taylor series expansion. Now, Taylor series, like we discussed, it gives us a sequence of polynomials that approximates a function within the disk of convergence. Now, if I increase the disk of convergence, I will get a pole of, or let's say a singularity of fz. Now, if fz has a singularity, approximating fx by fz by a sequence of polynomials doesn't make sense because polynomials are analytic. So I'm trying to approximate a function with singularity with a sequence of entire functions. So it doesn't make sense. So in that case, I will approximate fz by a sequence of rational functions. So what I'm trying to say is, I will say fz, and I'm trying to approximate this by a sequence of what is the sequence of rational functions minus right. So I am trying to approximate fx by a sequence of rational functions, and it should be of this order. This means the power series expansion for fz and the power series that I get from here, they should agree up to z to the power m plus n plus 1 term. So that this I say is a rational approximation. This is my condition. So which qm and pn to choose? I'll choose such qm and pn such that when I convert this rational function into, or develop this rational function into a sequence of, into a power series, this power series should agree with this power series of fz up to z to the power m plus n plus 1 term. So this is my condition, right? So this is the idea of rational functions. Fz is a function with singularity. I will not approximate with a sequence of polynomials because polynomials are entire functions, no singularity. So I will try to approximate fz by sequence of rational functions. But now but this is rational approximation. This is not Padet approximation. So, but see, the problem with this is I have to convert this qmz by p and z into a power series. It means I have to divide a polynomial by a polynomial, write its entire series, which is not computationally efficient. So what the Padet's idea was, it was started with Frobenius and it was continued in PhD thesis of Padet, right? So what he thought of is, instead of working with this fz minus qmz by pnz, let us linearize. So we will say, if this happens, pnz fz minus qmz is satisfies this, then if this is satisfied, then qmz by pnz, it converges to f of z. So the rational function that I obtained via this linearization is called the Padet approximation to fz. Now, what is the advantage of this over this? I don't have to divide polynomials in this case. I will just multiply. So this is the idea behind Padet approximation. So, so let us work. Let us start with a working example. So, so consider this. I'll end with this example. So fz is c naught by z plus c1 by z square plus c2 by z cube plus this. So this is a function which is analytic at infinity, vanishes at infinity, right? Because f of 1 by z vanishes at origin, so f of z vanishes at infinity. So now I want to approximate this power series or fz by a sequence of rational functions. So okay, before that, how do we even obtain? Let us. I'll come to this. Before that, how do we even obtain pnz and qnz? So what I have is, I want to approximate fz as c naught plus c1z plus c2z square by a polynomial qmz by pnz, right? So let us pnz, let us write pnz as z minus a to the power n plus a1 z minus a to the power n minus 1 plus a n minus 1 z to the power z minus a plus a n. There is a reason behind this way of writing the polynomial. Let us not go into it, because it is approximation at infinity, not at origin. So this is a better representation for polynomials if you want to approximate at infinity. So this into c naught plus C1Z plus C2Z square up to this. I want it to be equal to QMZ. So QMZ is V naught again of this form. Z minus A to the power M plus Z minus B1 Z minus A to the power M minus 1 plus Bm plus order of Z to the power M plus N plus 1. So this order of Z to the power M plus N plus 1, it means it is a polynomial, it is a power series that start with this term Z plus N plus 1 if you go into the theory. So what I will do, I will compare coefficients of, so this polynomial ends with degree m. This is a power series that starts with Z plus M plus N. So what are the power missing? I'll compare the coefficients of Z to the power M plus 1, Z minus A to the power M plus 2, and up to Z minus A to the power M plus N, because these are the terms that are missing on the right hand side. This polynomial ends with Z minus A to the power M. This is a power series that start with Z to the power M plus N plus 1. So these are the coefficients. So if you compare the coefficients of this left hand side, you will get a system of equation. The system of equation is this: C to the power M minus N plus 1, C to the power M minus N plus 2, C to the power M plus 1, C to the power M minus N plus 2, not power, C sub M minus N plus 3, Cm plus 2, Cm plus 1, Cm plus N into A naught, A1, An equals, since these terms are not on the right hand side, so I will get 0, right? So this way you will, so what is this? These are the coefficients of the polynomial P and Z. I will get the denominator. There is a way to construct the numerator also, but let us not go into it. So how it is related to continued fractions. So if I represent R, M, N, Z as QMZ by P and Z, I will get a table or array of Pade approximation. So what I have is R00, R01, R02, R10, R11, R03, R04, R12, R13, R20, R21, R22, R23, R30, R31, R32, R33, right? So how it is related to continued fraction? So consider this stairways. Right? If you consider this sequence of Pade approximation, for this sequence of, these are rational functions. Pade approximations are rational functions. So if you consider these rational functions, or this part or subsequence of Pade approximation, you will get a continued fraction expansion of this form: C naught plus A1Z by 1 plus A2Z by 1 plus A3Z and so on. Right? So again, what I say, we have computed Pade approximation for all degrees of M and N. I now arrange the Pade approximation in an array. If you give me this subsequence of Pade approximations, which are basically a sequence of rational functions, then these rational functions are the rational approximates of this continued fraction, and this continued fraction corresponds to fz. So from this sequence of rational functions, there are also the rational approximates that are obtained from this continued fraction, and this continued fraction also represents fz. So this is the relation of the approximation to continued fractions. So I'll stop with this, but I will end with the most popular continued fraction expansion, and this is this. So pi is 3 plus 1 by 7 plus 1 by 15 plus 1 by 1 plus so on, right? So basically this continued fraction expansion was obtained by let's say Aristotle, the Greek mathematicians. How it is obtained, not clear. If you search in textbook, you will find this. This is the so what are the approximates? So first is 3, second is 3 plus 1 by 7, third is 3 plus 1 by 7 plus 1 by 15, right? This gives you the rational number that we use to approximate pi. So this 22 by 7 comes from the continued fraction expansion for pi. This is 333 by 106, a much bigger number. So like we increase the order of rational approximation, we'll get a better approximation to pi. So 333 by 106 is always a better approximation to pi than 22 by 7. But since 22 by 7 is way much easier to use, we approximate pi by this rational function. So anywhere you see a rational number being used to approximate an irrational number, remember that there is always a continued fraction behind it. Okay, I'll stop here. Hope I have given you enough motivation to study continued fractions. And project ideas, continued fractions are, okay, let me stop sharing. How do I stop? Stop video. Okay, thank you. Okay, so project ideas, continued fractions are very, very, very important in number theory. The continued fractions that we discussed are very elementary. It contains the functions ai and bi's are polynomials, but if you go to continued fractions, they are special functions. They are used to different special functions. So in number theory, continued fractions are important. Ramanujan's work, a big part of his work is in continued fractions. Again, continued fractions, they have relations to the theory of moments. Moments play a very important role. They are related to orthogonal polynomials like Legendre polynomials, Hermite polynomials, and more practical applications. The moments of orthogonal polynomials, they are used in image processing. So there also continued fractions come into play in image reconstruction. So you have how do you reconstruct an image? You use the moments of orthogonal polynomials. So this is a big theory. You can go in this direction. Okay, I stop here. It's 5. Thank you all. Hope you at least have a motivation to study continued fraction in the future. Yeah, thanks. Samya. Jyoti.
Thank you, sir.
Yeah, Bhumika.
Yeah, now I request if there are any questions, you can use the raise hand button or okay, there's a question.
Yeah, Bharat.
Sir, yeah. So you were mentioning about the correspondence between continued fraction and a power series expansion. Like, if a continued fraction exists, then correspondingly we can find a power series expansion. So my question is that power series expansion convergent in some neighborhood, or it need not be in some cases as well?
Yeah, so there is a big convergence theory for continued fractions. So what we have discussed is correspondence. So this is the continued fraction, I obtain a power series, and this continued fraction corresponds to this power series. If we have studied let's say Fourier series expansion, this is what we say. This is a correspondence. This is a representation. But this correspondence or this convergence doesn't work for all BIs and AIs that we have considered, right? Or for all CIs, the coefficients of the power series. So we need to impose some conditions on AIs and BIs that appear in the continued fraction so that it converges to a power series. And again, whenever we talk of convergence, there will be domains. There will be precise domains in which the continued fraction will converge.
Also, one more question is like, for which kind of functions continued fraction representation exists? Like, does it exist for any given function, or is there any special criteria or characterization?
See, one big class is if you have a power series representation, you have a continued fraction expansion. We have seen that.
Yeah.
Right. So so there are special functions. Special functions means let's say tan, cos, sine, log, exponential. We have power series. We have a continued fraction expansion. But for gamma function or beta functions, their power series doesn't exist, but still, I mean, I don't think there is a very clear-cut answer, but if we have special functions, there's a class of functions called special functions, like trigonometric functions, hyperbolic functions, inverse trigonometric functions. They have continued fraction expansions. So for so for certainty, I can say if the function has a power series expansion, it has a continued fraction expansion.
Yeah. Okay, sir. Thank you.
Thank you. Yeah, any questions? Okay. Bhumika?
Yes, sir.
So thank you all.
Okay, so there are no questions. Okay. Thank you so much, sir. It was really a good session. You showed us a different world of continued fractions.
Yeah.
Thank you all for being there and obeying all the rules and regulations. Now it's time to capture this moment. I request everybody to turn their cameras on so we can have a group photo.
Hey, Tamagna.
Okay, I'll count up till 3 and then we'll have 1, 2. Thank you, everyone. Feel free to exit now.
Mm.
Thanks.